So hello, Mr. Watts here. Today we're going to consider a lesson about types of functions and inverses of those functions. So the two learning inquiries for today are what is a function and what are the different types. We're also going to consider why types of function are important when we're going to find an inverse function. Just to start you off with, here are three functions. We've got f of x, g of x and h of x are all different functions of x. You might want to pause the video here and try working out the inverses of these three functions. Okay, the solutions to those are looking like this. So for f of x, the inverse function would be half x minus a half. For g of x, the inverse function would be natural log of x minus 5. And h of x is an interesting one. The inverse function of h of x would be 10 over x. This is actually the same thing as the h of x function itself, so we would call this a self-inverse. We'd like to think about these things graphically this time. So if we think about these things graphically, there is a relationship between the two things. So this is the first one for f of x and the inverse of f of x. We've got a similar image for g of x and a similar image for h of x. So there is a link between the function and the inverse for the first two and the function itself for the third one, and that is a reflection. So in all of these cases, there is a reflection in the line y equals x. So f of x reflects onto f to the minus 1 of x in the line y equals x. G of x goes to the inverse of g. With h of x, it's a little bit different. It's actually symmetrical in that line already. So if we reflect it, we get the same curve, which is why it's coming out as being a self-inverse. And this feature is true for any function and its inverse. If you actually think about the steps to working out an inverse function, we swap over y and x after we've done our rearrangement. And that's what this mirror image is doing. It's this swapping the y values for the x values. If we think about this as well in terms of domain and range, so this is the middle example from the previous page, e to the x plus 5. The domain of e to the x plus 5, x can take any value e to the x plus 5 and we could calculate it. So x can be any of the real numbers. The range, though, is restricted. The smallest value we would get, it would tend towards 5, so the range would have to be anything greater than 5. And the interesting thing is, if we're considering this mirror image and this idea of x's and y's swapping over, if we consider the inverse function, the domain of the inverse function matches up to the range of the function itself. So because the function had to be greater than or equal to 5, the domain of the inverse function x has to be greater than 5. And you can see that on the graph. The range, because the domain of the actual function could take any real value, the range of the inverse function can take any real value. So the two things have swapped over. So the domain and the range, what we had for those ideas in the original function, have swapped over, and what was for the domain is now for the range, and what was for the range is now for the domain. The two things have switched. So the first type of function we're going to consider is a one-to-one function. They are referring to the x values and y values. So a one-to-one function has one x value to every one y value. An example of this could just be a simple straight line curve, y equals x to minus 2. Every x value has a separate unique y value. We could also represent this as a mapping, instead of graphically, where we're subtracting 2. So the values on the left would map onto the values on the right. We can also have a many-to-one function. So this is where many different x values map onto a single y value. So in a many-to-one function, two or more x values parts of the domain map onto the same part of the range. So y equals x squared is a fairly simple example of this. So if you just consider if we had when x is minus 2, the y value, the range value is 4. We also could have x is positive 2, the range will be 4. We're getting two different x values mapping onto the same y value. So many x values can give us the same y value. In this case, two different x values can give us the same y value. If we consider one to many, so one x value to many y values, okay, we could consider square root to be one to many. If we square root something like 25, the answer could possibly be 5, or it could have been negative 5. And that would actually graph out looking something like this. So square root, we could have one x value, and then we have many different y values, two different y values that come out. The thing to watch out for this is we would not actually define this as a function. Okay, we don't like this ununiqueness of treating the square root in this way. If you type in square root of 9 on your calculator, it will tell you it's 3. Okay, we like to have a unique answer. We don't like to have these two different possible things coming out. So treating square root x like this, we would not consider it to be a function. But as we just mentioned, we could consider making it a function as long as we say that the answer we only take is the positive answers. So if we consider square root, which is what we usually do, just to be the positive answers, then we'd have a curve that looks like this, and then it would actually be a one-to-one function. So if we want to consider things as functions, we sometimes need to put these restrictions in place to allow that to happen. We're now considering square root in this way, where there's one unique answer coming out for one input. So let's have a think about how this links to inverse functions. So we can't actually find the inverse for all these different types of function. And this is because the inverse may not actually turn out to be a function. It may be like that example of one to many. We don't like that coming up in functions. So if the answers are coming out like that, we can't class it as a function, so we've got a problem. So let's consider this graphically to see how that works out. So to consider this point, we're going to think about the curve of y equals x squared. If we think graphically, the inverse function would be a mirror image in the line y equals x. So if we mirror the curve y equals x squared, we would actually come out with an unusual looking curve like this. And if we think back to our definition of a function, this would not actually be classed as a function. We could draw on a vertical line, it will cut the curve twice, we're getting two different solutions for our one input. So we've got a problem here. So we can't find the inverse as it stands of y equals x squared because we come out with something that's not a function if we do consider the graphical inverse of it. So this would be true for any many-to-one function. We could only find the inverse of one-to-one functions. So let's think about what we could do. So instead of considering the whole curve for y equals x squared, we can restrict the domain and just consider part of the curve. So here's one way we could do that. This is just considering when x is greater than 0 on the y equals x squared curve. If we consider the mirror image, that will give us this, which would just be the curve of y equals the square root of x, just the positive solutions to the square root of x, and now that nice and tidily fits. There is another option we could consider. We could consider when x is less than 0, and that part of the x squared curve. The mirror image of this would look like that, and this would be the negative square root of x solution. So these are our two options we can do. So if a curve is many to one, we can't find the inverse as it stands, but we can restrict the domain to just part of the many to one curve for a section of it which is one to one, and then the inverse for that one will exist. But we are going to have to think about carefully what our solution to that would be. So first we're going to try a fairly basic example. We've been asked to choose a suitable domain and then find the inverse function for f of x equals x squared plus 8x plus 11. I'm giving you a hint that completing the square is the best place to start. So if we have a go at completing the square, we should be coming out with the f of x. We should be going for x plus 4 all squared, because the plus 4 is half of the coefficient of x, which was 8. If we expand in this bracket, we get x squared plus 8x plus 16. Because we only want plus 11, we're going to have to minus 5 from that to make it work out. And we can use this complete square form to sketch the curve, which would look something like this. So from what we talked about before, if we're going to restrict the domain, the vertex down here is the important point. And that vertex is going to have coordinates of -4, -5. So if we're going to restrict the domain, we've got two choices. I'm going to go for the positive side, so let's restrict our domain that x has to be greater than -4. We can consider the other solution after we've finished. So we're just considering this half of the curve, kind of in this direction. So we've decided how we can limit it to make it one-to-one. So if we now consider doing the rearrangement to figure out what the inverse function is going to look like, if we start with y equals x plus 4 all squared minus 5. So we'll add on the 5 first. So y plus 5 is x plus 4 all squared. This is the bit we need to be careful with and take into account. So to remove the squared from the right hand side, we need to square root. And we're adding in the plus or minus sign, because at the minute we've not considered if we want the positive square root or the negative square root. And then to finish off, we're going to subtract the 4. So I'm probably going to go for writing it as -4 plus or minus the square root of y plus 5. So we've set this up, but we do need to carefully consider if we want the positive square root or the negative square root. If we think about the curve we've sketched and how that would end up getting mirrored, so the minimum point is going to end up somewhere over here. Where it crosses the mirror line would match up, and then another good point to do, this point up here would be 11, so that is going to get mirrored down here to be 11 as well. So we're going to end up with our curve doing something along these lines. So that looks like a positive square root curve to me, so we're going to have to choose the positive value. So we also want to swap the y's and x's over. So for our inverse function, f to the minus 1 of x, we're going to go for -4, and we want the positive square root. And we've swapped the y's and x's, so we're going to go for x plus 5. So that would be our inverse function with our restricted domain of x being greater than -4. If we did go for the other choice and we picked the other side of the curve and went for when x is less than -4, then we would want our inverse function to be -4 minus the square root of x plus 5 instead. So here is a slightly more advanced example. We are still choosing a suitable domain and then finding the inverse function for a quadratic, but this is a slightly trickier quadratic this time because there is a coefficient of x squared. We're still going to try and complete the square, so that coefficient of x squared is what we need to deal with first. So we're going to take that -2 out as a factor. That's our first job. I'm going to leave the -7 on its own. We don't need to take the factor of 2 out of that term if we don't want to. So from here we can now complete the square for the two terms inside this bracket. I've left the other bits alone. So this is going to end up being x minus 2 all squared. If we expand it out, x minus 2 all squared, we would get the x squared that we want, we'd get the -4x that we want, but we'd also get plus 4, so we're going to have to minus 4 to take that into account. And if we tidy things up from here, we would end up with -2 x minus 2 all squared. If we multiplied out the -2 with the -4, that would make +8. And then we've got subtract 7 on the end, so we're going to be left with +1. So here is our completed square version. If we use that to sketch the curve, it should look something like this. And the key point that completing the square can tell us is that the maximum point this time is going to be with coordinates of 2, 1. We've got a maximum point because it's a negative coefficient of x squared, giving us the characteristic shape. So if we want to think about our inverse function, we need to restrict our domain because it's many to 1. So if we go for when x is greater than 2, we are just considering the right-hand side of our curve, and this bit going down here. If we consider what the mirror image of that would look like, if this has coordinates 2, 1, the mirrored point would be 1, 2. It's crossing the x-axis at a bit less than 3, so do the same up here. So it's going off in this direction somewhere, roughly around here. So again, we're going to need the positive square root to make it match up to that kind of curve. So if we're trying to find our inverse function, let's start writing it as y equals . So our first job will be to subtract the 1, and we can divide by -2. I'm quite tempted to tidy this up because we've got -1 and -2. We could multiply top and bottom by -1 to make it 1 minus y over 2. And to remove the squared, we are going to need to square root. And we've already decided that we want to use the positive square root, not the negative square root. So we've nearly finished our rearrangement. If we try and write it in the correct notation, so if we're going for f to the -1 of x, that is going to be, because we have this -2 on the end here, we need to +2, and then we're going to add on the square root of 1, and we've swapped the x's and y's, so 1 minus x over 2. So this would be our inverse function when we're dealing with the x is greater than 2. The other choice we'd have is if we decide to deal with when x is less than 2, that will be the other half of the curve, and we need to use the negative root. So for that half of the curve, we do f to the minus 1 of x equals 2 minus the square root of 1 minus x over 2. And the reason we're having to take these things into account is because our starting function was many to 1. We've had to restrict the domain to make it 1 to 1 and consider the implications of that on our inverse function. So as a quick plenary task to sum up, you should be able to consider for yourself these questions. So what are the different types of function that you are supposed to be aware of that we've discussed? Do you think you could sketch a function that's 1 to 1, a function that's many to 1, or a graph which we wouldn't actually class as being a function? Could you give some different examples of these? What's the link between this part of maths of considering types of functions and finding inverse functions? Okay, why is this important? Why do we need to take it into account? Okay, and then the key things to remember, so functions have to be 1 to 1 for us to be able to find their inverse. If we're interested in the inverse of a function that is many to 1, we have to go through this step to start with of restricting the domain. Or if it's an exam question, it may be restricted for you, and you need to look at that carefully. The most common applications that you'll come across at the moment are inverses for quadratics, where the domain's been restricted and we decide between a positive square root and a negative square root. Later on in the course, you will look at inverses of trig functions and how we need to restrict domains to choose those. Okay, thank you very much. I hope you found that useful.